Assalamualaikum and hi everyone! We are Group 2 from CDCS 143, and before we begin our presentation on application on mechanics in real life, allow me to introduce our group members. Firstly, we have Nur AQILAH IZZATY ZAINUDDIN 2023856432. Next, we have Nur HUSNINA HISHAM 2023874894. Our third member is UMMI RAUDHAH MARZUKI 2023647826. And lastly, myself, MUNIRAH ASRI 2023879892. These are the contents that we will cover: introduction, Newton's law, types of forces, and application of Newton's law.
In kinematics, we learned that knowing an object acceleration, initial position, and velocity allows us to predict its future motion. However, what wasn't discussed was the cause of this acceleration. For example, when a piece of chalk is dropped, it accelerates downward due to gravity. The force of gravity from the earth pulls the chalk towards its center. This shows that acceleration is always caused by a force. Newton's law of motion explains how force affects the motion of objects. The area of mechanics that deals with the effects of force on motion is called dynamics. This chapter explores all three of Newton's law of motion and how they apply to problems involving constant velocity, acceleration, friction forces, and static equilibrium in concurrent force systems.
Newton's law of motion are three statements describing the relations between the force acting on a body and the motion of the body, first formulated by English physicist and mathematician Isaac Newton, which are the foundation of classical mechanics. We move to the Newton first law of motion. Newton's first law of motion can be stated as a body at a rest will remain at rest, and a body in motion at a constant velocity will continue in motion at a constant velocity unless acted on by some unbalanced external force. Newton's first law of motion is also called the law of inertia. Inertia is the resistance of a body to a change in its motion. The mass of a body is a measure of its inertia, and the SI unit for mass is in kilogram. And the greater the mass of a body, the greater its inertia. For example, walking on a slippery surface such as ice can lead to loss of traction. If you suddenly stop on ice, your body's inertia will continue to carry you forward, causing you to slip and fall. The second law of motion can be stated as the rate of change of momentum of a body is directly proportional to the resultant force on it and is in the same direction as the resultant force. Newton's second law is represented by the expression F equal to d over dt multiplied by mv. But if the mass of the body is constant, then F equal to m multiplied by dv over dt equal to ma. For example, throwing a ball. When you throw a ball, the force exerted on it determines how fast it accelerates and how far it travels. Applying a greater force to the ball will result in a higher acceleration and a longer throw. Newton's third law of motion means whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Every action force in nature, there is an equal and opposite reaction. If object A exerts a force on object B also exerts an equal and opposite force on object A. In other words, F1 equal to negative F2. For example, jumping on a trampoline. When you jump on a trampoline, the trampoline surface pushes against your feet with an equal and opposite force, propelling you upward. The harder you push against the trampoline, the higher you will bounce. Move to the problem statement 1. Ahmad has a younger sister. His younger sister's name is Amirah. Every evening, Ahmad would accompany his younger sister to play at the playground. His younger sister loves to play sliding. The surface of sliding at 35 degrees with the horizontal end mass of his younger sister is 55 kg. Find the acceleration of his younger sister and the normal force. We have 3 steps to solve the problem statement. In step 1, we start by drawing and labeling the free body diagram of Amirah as she slides down. The diagram shows all the force acting on her body. Her weight acts straight down due to gravity, but because the slide is tight at 35 degrees, we break the weight into 2 components. One component acts down the slide and causes her to move. This is called the parallel component. The other acts into the slide, and this is the perpendicular component. The surface of the slide pushes back with a force called the normal force, which balances the perpendicular component. Move to the second step. First, Wx equal to mg sin theta, which is 55 multiplied by 9.81 and multiplied by sin 35 degree. So we got the answer Wx equal to 309 Newton. Then the Wy is equal to mg cos theta, which is 55 multiplied by 9.81 and multiplied by cos 35 degree. The last step is find the acceleration using formula F equal to ma and normal force using R equal to mg cos theta. To find acceleration, we use Fx equal to ma, which is mg sin theta equal to ma. As we know, the mass of the body is 55 kg, so we replace m by 55, so we got 309 equal to 55 multiplied by acceleration. Then, the acceleration is 5.61 ms negative 2. After that, to find normal force, we use R equal to mg cos 35 degree, so the answer is 442 Newton.
A force is basically a push or pull acting on an object. It can make an object move, stop, change direction, or even change its shape. We measure force in newtons, named after Sir Isaac Newton. The formula is F equal to ma, which means force equals mass multiplied by acceleration. So, the heavier an object is, or the faster it accelerates, the more force is needed. There are 2 main types of forces: contact forces and non-contact forces. Contact forces require objects to physically touch. Examples include friction, tension, and the normal force. Non-contact forces, on the other hand, act from a distance, meaning the objects don't need to touch. These include gravitational, magnetic, and electrostatic forces. Let's begin with gravitational force. This is the attraction between any 2 masses. We experience it every day as weight, which is the gravitational pull of the Earth acting on our body. The formula is W equals to mg, where m is mass and g is gravitational acceleration, approximately 9.81 meters per second squared. For example, when you drop an object, gravity pulls it downward. That's gravitational force in action. Now let's look at normal and frictional forces. The normal force is a support force. It acts perpendicular to a surface, pushing upward against gravity. For instance, when a book rests on a table, the table pushes up with a normal force. Frictional force opposes motion. It acts parallel to the surface and prevents objects from sliding easily. The strength of friction depends on the surface texture and the normal force. Think about how it's harder to push something on carpet than on tiles. That's friction at work. Next, we have non-contact forces, magnetic and electrostatic. Magnetic force happens between magnets or magnetic materials. For example, when you bring 2 magnets close, they either attract or repel. Electrostatic force occurs between charged particles. Of one example is when you rub a balloon on your hair, the balloon becomes charged and sticks to a wall. That's electrostatic attraction. Moving on to tension and applied force. Tension is the force transmitted through a string rope or cable when it's pulled. For instance, if you're holding a bucket with a rope, the rope is under tension. Applied force is any force you apply directly, like pushing a chair or pulling a box. Often, applied force and tension work together, like when you're pulling something with a rope. To better understand how multiple forces act on an object, we use a free body diagram or FBD. In an FBD, we draw arrows to show all the forces acting on an object, including gravity, normal force, friction, tension, and applied force. This helps us analyze the object's motion or determine if it's in balance. It's a crucial tool in physics problem solving. Forces play a huge role in everyday life and engineering. In engineering, we use forces to design safe bridges, buildings, and machines. In sports, athletes rely on the right force to run, jump, and balance. In transport, forces are involved in things like braking, air resistance, and engine power. Even simple actions like walking, lifting, or pushing involve forces working together. To summarize, forces are everywhere. They help us understand how objects move, how structures stand, and how to make things safer and more efficient. They are the foundation of mechanics and a key part of our daily life, whether we realize it or not.
First thing in applications of Newton's law is free body diagram, which is FBD. Free body diagram is a force diagram showing all elements in the diagram, such as axes, vectors, components, and angles. There are 5 steps to draw the FBD. Here are the steps to draw a FBD. The first one, we need to draw a sketch. Second, for one object, draw a FBD showing all the forces acting on the object. Make the magnitudes and direction as accurate as you can. If there are multiple objects, draw a separate diagram for each one. The third, resolve vectors into components. We need to use trigonometry. The fourth, apply Newton's second law to each component. And lastly, we can solve it. First of all, I will show you a FBD involving horizontal surface. Here is the example of FBD. The image displays a block subjected to various forces and its corresponding free body diagram. The first image shows a block at rest or in motion on a surface. The second image is the free body diagram, which simplifies the force acting on the object by representing them as vectors originate from a single point. Next is the FBD involving inclined surface. An object sliding down an incline has 3 forces acting on it. The first one, the normal force. This force is always perpendicular to the surface. The second one, the gravity. This force is always pointing downward. The third one, the frictional force. This force is always... Next is the FBD involving inclined surface. An object sliding down an incline has 3. This image illustrates the forces acting on an object on an inclined plane, a common scenario in physics problem related to Newton's law of motion. For motion, this arrow indicates the direction in which the object is moving or intending to move along the inclined plane. I will show you the application not involving frictional force. Not involving frictional force means that the situation where motion or action occurs without any resistance between surfaces. For example, object in space, vacuum, moving without air resistance. Here is the example of problem statement. The topic is about free fall in a vacuum. An astronaut drops a small tool inside a vacuum chamber on the moon, assuming no air resistance and that the acceleration due to gravity on the moon is 1.6 meter per second square. Calculate how far the tool falls in 5 seconds. To solve this problem, we need to use the formula for displacement in free fall, which is S equal to 1 over 2 gt squared. The given information was g equal to 1.6 meter per second square and t equal to 5 seconds. After we get all the information, we need to substitute the value into the formula, which will be S equal to 1 over 2 times 1.6 times 5 square equal to 0.8 times 25 will be equal to 20 meters. So the final answer will be the tool falls 20 meters in 5 seconds. Then I will show you about the application involving frictional force. The meaning of involving frictional force is where a situation where motion is affected or enabled by resistance between surfaces. For example, we walking or driving where friction prevents slipping. Here is the example of problem statement involving frictional force. The topic is about braking distance of a car. A car is traveling at 25 meters per second on a dry road. The coefficient of friction between the tires and the road is 0.65. If the car suddenly applies its brake, calculate the distance it will travel before coming to a complete stop. Assume no other forces act on the car besides friction and take G equal to 1.8 meter per second square. I will show you how to solve this problem. First, we use the work energy principle or the kinematic equation, V square equal to U square plus 2AS. The information given, V equal to 0, because the car is at rest or stop. U equal to 25 meter per second. And then we need to find the value for acceleration, which is A equal to negative mu G. The value for mu and G is already given. Mu, which is coefficient of friction, is equal to 0.65. G is equal to 9.8. Then we will substitute the value into the formula, which negative 0.65 times 9.8 will be negative 6.37 meter per second square. That will be value for acceleration. Now let's solve for displacement S. After we get all the value, we need to substitute the value into the kinematic equation. Then it will be 0 equal to 25 square plus 2 times negative 6.37 S. Then it will be negative 625 equal to negative 12.74 S. And to find the value of S, will be 625 divided by 12.74, and we get the value of S, which is 49.07 meters. So the final answer will be the car will stop after approximately 49.07 meters.
Work is divided into 3 parts. Now, I'm going to tell you about the first one, which is work done by a constant force. First formula is W equal to Fs, where F is stand for force and S stand for displacement. This formula is using for finding the work done when force and displacement in the same direction. Next, formula is used when force and displacement in different direction, which is W equal to force multiplied with cos theta multiplied with. Next, we have work done against gravity. The formula for work done against gravity is W equal to mgs, where m is mass, g is gravitational force, which is 9.81, and S stands for displacement. Okay, first example. Find the work done against gravity when an object of mass 3.5 kg is raised through a vertical distance of 6 meters. Let me explain to you how to solve this question. First, we know that the formula is W equal to mgs, where m is 3.5, g is 9.81, and S is 6. Put together the information given into the formula. We have 3.5 multiply 9.81 multiply 6, and the answer is 206.01 joule. Now, we're gonna talk about work done against friction. When a body is pulled at a uniform speed on a rough surface, the work is done against the frictional force which is acting on the body due to the contact with the rough surface. I will explain to you about the condition when no work is done. First, object is stationary. Next, no force is applied. And last but not least, direction of motion is perpendicular to applied force. Now, energy. We have kinetic and potential energy. Kinetic energy is ability to do work by virtue of having speed. Formula for kinetic energy is kinetic energy equal to 1/2 mv squared, where m is mass and v is velocity. Next, potential energy is ability to do work by virtue of positions or condition. For Formula for this one is potential energy equal to mgh, where m is mass, g is gravitational force 9.81 and h is height. Now, power. Power is a measure of the rate of which work is being done. Problem solving. Step first, we know that formula for kinetic energy is 1/2 mv². First, we need to calculate the kinetic energy for Hafizah. We need to substitute all the information given in the table into formula, where 54 is mass for Hafizah and 7.8 is the value for Hafizah's velocity. 1/2 multiplied with 54 multiplied with 7.8 squared. The answer is 1643 joule. Next, we have Alifah mass 70 kilogram and her velocity is 5.9. Same step that we use to calculate the kinetic energy for Hafizah. Just substitute all the information. 1/2 multiplied with 70 multiplied with 5.9 square. The answer is 1217 joule. From the answer above, we can conclude that Hafizah has greater kinetic energy compared to Alifah.
In conclusion, understanding forces helps us explain how objects move and interact in real life. By using formulas like F equal to ma and W equal to mg, we can calculate force and weight easily. Knowing different types of forces like friction, tension, and normal force allows us to analyze everyday situations more accurately. These concepts are not just for theory, but also help us solve real problems in areas like engineering, balance, and structure.